we have these two new tools, kinetic friction and static friction. And now I want to actually use these in an example. So I'm going to do a first example that'll be really straightforward and simple, and then I'll do a more complicated example in a later video. Let's do this one first. Here's my block. Let's make this thing 5 kilograms. It's sitting on a table. Let's put our pulley here, because why not? And then we'll make a weight that hangs down from the table. This is starting to be familiar. And just to make sure that we don't run into the table, let's do that. We'll put over here a coefficient of static friction of 0.8, kinetic friction of 0.2, and we'll make this thing be, let's have this be 4 kilograms. We're going to have to attach this by rope. The rope continues even through the writing. It's just going to pass behind the writing. I would like to know, find the acceleration. I've got to connect these by a rope. Rope comes in, it's passing behind the writing. And I would like to know, 1, find the mass needed. So find the mass M needed to get this system moving. And then 2, once it's moving, find the acceleration. Here we go. I'm going to start with a free body diagram. That is a good place to start. So for the block, this thing's got a mass of 5 kilograms. I'm going to want that label later on anyway, so there it is. Here are my forces. Straight down, M1G. Straight up, normal force from the table. To the right, I have a tension force. And that's what I had before when I did this problem, but now, to the left, I also have a force. As this thing wants to start moving to the right, it's going to feel a friction force to the left, and that is a static friction force. This whole system moves horizontally. I'm going to call to the right my positive x-axis, which means I'm going to call upward my positive y-axis, circle that guy, put a box around the whole thing. And that looks like a pretty promising free body diagram. Now for the triangle. The triangle has mg going down. It has tension going up. I need to keep track of my axis. What I had over here was this axis. That curves over my pulley, so I have to have downward be my positive x-axis here, and to the right be my positive y. Circle that thing, put a box around that hole. Free body diagram, and I'm going to label this one just capital M. There we go. I'm looking for the mass needed to get this system moving. That's my first question. For the box, I have x direction forces that look like this. I'm going to say my sum of forces in x equals, I've got tension to the right, I've got friction to the left, and that's it. So it equals m1 times acceleration. That's acceleration in the x direction. Friction, I will have to come back to right now. Actually, if I'm looking at my maximum, if I'm looking at my threshold situation, I want to put a minimum amount of weight on that triangle. I want that triangle to have the smallest amount of mass possible to get this system to move. This system is not going to move until I have met my static friction limit. So what I would like to do is look at my static friction max. My static friction max is equal to mu static times the normal force, but I'm one step ahead of myself because I don't know that normal force yet. I'm going to need to look at the y direction for this. Sum of forces in the y direction, I have the normal force going up. I have m1g going down equals m1 times ay. Acceleration in the y direction had better be 0. If it's positive, then I'm levitating off of my table. If it's negative, I'm sinking into my table. I need that to be 0. So when I solve for my normal force is equal to m1g. That's nice. I'm going to take this value and plug it in there. So now when I do that, continuing on with my playbook, I get that my sum of forces in the x direction are tension minus mu static times m1g, remember that was my normal force, equals m1 times ax. Ax, if I'm not accelerating, Ax is going to be 0 if I'm looking at that threshold case. So what I have, tension minus mu static m1g equals 0. Tension equals mu static m1g, and we can plug in some values. I had a 0.5 times 5 kilograms times 10 meters per second squared. 5 times 10 is 50. Half of that is 25 newtons. I need 25 newtons of tension to be able to make this thing work. I wasn't asked to find the tension. What I was asked to do was find this mass. So for my triangle, sum of forces in the x direction says I've got an mg minus a tension force that I now know equals ma. That is an ax. I already know my ax, that's still 0, because I'm looking for how the system just barely doesn't move. So when I solve this, I get m equals t over g, 25 newtons over 10 meters per second squared. I get a minimum mass of 2.5 kilograms. Before, when I didn't have friction, any amount of mass would have gotten the acceleration. Now I need to overcome friction, so I have to give this enough. And the second part of this question says, once it's moving, find the acceleration. So now what I want is to say, I have this system that's just barely hanging on, right? Like my static friction is just barely enough to hold this together if I put 2.5 kilograms on that triangle. If that triangle is 2.5 kilograms and I breathe on it, now I have surpassed static friction and this thing will be moving. So the way that's usually worded is the system is bumped from rest, or the system is nudged from rest. Some kind of word that effectively means we're going to get this thing going, but just barely. Once this thing's moving, what changes is very little. This F static will become F kinetic instead, and everything else stays the same. So, going over here, my F static becomes an F kinetic, but my acceleration is no longer 0. I'm going to start writing these equations to the side. I'll just make a copy of this. and then we can run with that. So, free body diagrams for the very, very different case of kinetic friction. I'm looking over here. I know I'm going to need both my x and my y. Let me do my y first this time. Sum of y forces, I'm going to get n minus m1g equals m1 times acceleration in the y direction. Acceleration in the y direction still has to be 0, same reason as before. Normal force equals m1g equals 5 kilograms times 10 meters per second squared. That is 25 newtons. Okay, x direction. This is all for the box. X direction. I'm going to have tension minus friction, and my frictional force is mu k times the normal force, because I'm looking at kinetic friction, equals m1 times acceleration. The system's moving, so the tension has changed. The acceleration is different because it's no longer 0, so those are both unknowns. Alright, 2 unknowns in there. I'm going to have to go to my triangle. For my triangle, my sum of forces in the x direction is going to be mg minus t equals m times a. Same idea, sum of forces equals mass times acceleration always. I now have 2 equations with 2 unknowns. I'm going to add them up. Left side, tension minus mu k, the normal force was m1g, mu k m1g. That is the first equation, plus second equation left side, mg minus t equals first equation right side, second equation right side. The t and the t cancel, which is great. It means that acceleration is going to be my only unknown. I'm going to factor it out like I always do. And over here, I'm going to be left with, I'm just going to write the positive one first, mg minus mu k m1g. Solving for acceleration, I get mg minus mu k m1g over m1 plus m2. So when I plug those values in, I get 2.5 kilograms, 10 meters per second squared. I'm going to move this up. Minus the coefficient of kinetic friction was 0.2. And then divided by the total mass, which was 2.5. Well, mass 1 was 5 kilograms. Mass 2 was 2.5 kilograms. And that works out to be 2 meters per second squared. I get some form of what's on top of here, mg minus this resistive force, so I get some form of a drive force on top, and on the bottom I get total mass. But that's it. I combined my same ideas. I had to make the very difficult switch in my free body diagram from static friction to kinetic friction. Other than that, everything stayed the same. Went through my whole process. When it was static, my acceleration in the x direction had to be 0. Once it's kinetic, my acceleration in the x direction does not have to be 0. But that's the whole process.